A single F-35 Lightning II costs approximately $100 million. However, the total life cycle cost of the program is projected to surpass $1.7 trillion, making it the most expensive military project in human history. To put that in perspective, this single aircraft program costs more than the annual GDP of countries like Spain or Australia. This investment does not just buy a faster or more agile aircraft. In fact, many older platforms can outmaneuver the F-35 in a traditional dogfight. The Pentagon did not build this machine to win a 1940s-style air battle. They built it to eliminate the concept of the dogfight entirely. The F-35 functions as a central node in a digital network, gathering and distributing intelligence across an entire theater of war. It uses 8.6 million lines of code to manage flight controls, sensor fusion, and the weapon systems, more software than the Space Shuttle or the original Boeing 747. Pilots now wear a helmet priced at $400,000, which allows them to see through the very fuselage of the jet using 6 high-definition infrared cameras. This technology changes the pilot's role from a traditional aviator to a systems manager operating at Mach 1.6. But as the global fleet grows, a critical question remains. Can a machine this complex survive the harsh realities of a sustained, high-intensity conflict? Or has the quest for technological perfection created a platform too expensive to lose? The F-35 program operates on a scale that redefines military-industrial planning. Lockheed Martin designed 3 distinct variants, the A, B, and C, to replace a wide array of specialized aircraft, including the F-16, A-10, and F/A-18. This joint approach aimed to save money through parts commonality, but the reality resulted in a logistical challenge involving over 300,000 individual parts per aircraft. Economically, the numbers are staggering. While the flyaway cost for an F-35A has dropped to roughly $82.5 million in recent lots, the operating cost remains the primary hurdle. Flying a Lightning II costs approximately $30,000 to $42,000 per hour, depending on the variant and the year of the data. Over a planned 66-year lifespan ending in 2088, the U.S. military expects to spend $1.3 trillion just on maintenance, fuel, and upgrades. This financial commitment forces a strategic shift. Military planners are no longer just buying a plane, they are investing in a 50-year technological roadmap. The Block 4 upgrade alone, which improves the jet's processing power and weapons capacity, carries a price tag in the billions. This massive investment ensures that Allied air forces stay ahead of modern surface-to-air missiles, but it also creates a too-big-to-fail scenario for Western defense. Engineers had to balance these costs against the requirement for a multi-role platform that can strike ground targets, conduct electronic warfare, and engage in air-to-air combat simultaneously. Every dollar spent on the F-35 is a bet that information dominance will win the next war. Massive investment brings massive risk, but what exactly are the Air Forces paying for at $100 million per airframe? The answer lies beneath the surface in a geometric design that makes a 51-foot-long jet appear no larger than a golf ball on a radar screen. The engineers achieved the F-35's stealth capability through a combination of precise physical geometry and advanced material science. Traditional fighter jets carry missiles and fuel tanks under their wings, creating radar traps that reflect signals directly back to enemy receivers. The F-35 eliminates this by housing its entire payload within 2 internal weapon bays. When the doors are closed, The aircraft maintains a clean, jagged-edge silhouette designed to deflect radar waves away from the source rather than reflecting them. The skin of the aircraft is coated with radar-absorbent material, RAM. Unlike the delicate high-maintenance tiles used on the older F-22, the F-35 uses a more durable fiber mat skin. This material works at the molecular level to trap electromagnetic energy and convert it into heat. The precision of the assembly is so critical that the gaps between panels must be measured in thousandths of an inch. Any misalignment or a single loose screw can increase the jet's radar cross-section, RCS, significantly. Strategic stealth also involves managing the heat signature. The Pratt & Whitney F-135 engine produces 43,000 pounds of thrust, generating immense thermal energy. To hide from infrared sensors, the jet uses fuel as a heat sink, circulating it through the wings to cool the internal systems before it reaches the engine. The exhaust nozzle is also serrated with edge-aligned teeth to mix hot air with cold, ambient air more rapidly, reducing the heat trail visible to heat-seeking missiles. This physical invisibility allows the F-35 to penetrate deep into contested airspace without being detected by traditional S-400 or S-500 air defense systems. However, stealth is not just about being invisible to the eye. It is about managing every emission coming from the jet. Hidden shapes grant invisibility, yet the most dangerous part of the jet isn't its skin, but its brain. Block 3. The flying supercomputer. The F-35 does not just fly, it processes. At the core of the aircraft is the Integrated Core Processor, ICP, capable of performing over 1 trillion operations per second. This brain manages the process of sensor fusion, where data from multiple sources, radar, infrared cameras, and electronic warfare suites, is combined into a single, unified picture for the pilot. Instead of looking at 3 different screens to identify a target, the pilot sees one clear tactical map. The jet's primary eyes are the AN/APG-81 AESA which can track multiple ground and air targets simultaneously, while remaining difficult for enemy sensors to detect. This is complemented by the Distributed Aperture System, DAS, 6 infrared cameras mounted around the fuselage. The DAS provides a 360-degree sphere of situational awareness. If a missile is launched from miles below or behind the jet, the computer identifies it, tracks it, and projects a warning directly onto the pilot's visor. This level of integration is managed by 8.6 million lines of software code. To ensure the pilot isn't overwhelmed by this data flood, the system uses priority logic to highlight only the most immediate threats. But the vibration of the cockpit and the hum of the cooling systems are the only physical reminders that this supercomputer is flying at Mach 1.6. The pilot no longer dogfights with a stick and rudder. They manage a battlefield from a digital throne. If you're enjoying this deep dive into military technology, consider subscribing to the channel. And before we continue, leave a comment telling us which country you're watching from. It's always fascinating to see how these machines capture attention from people all over the world. Pilots no longer look at screens. They see through the floor of the jet. But can a human mind process that much data? While the software handles the information, a different set of physical laws governs the most complex version of this aircraft, the one that can stop mid-air and land on a postage stamp. The F-35B variant performs a feat of engineering that seems to defy the laws of aerodynamics. It can stop in mid-air and descend vertically. To achieve this, engineers integrated the Rolls-Royce lift system, a massive counter-rotating fan located directly behind the cockpit. When engaged, a clutch connects the main F-135 engine to this fan via a drive shaft that delivers 29,000 horsepower. The fan sucks in cold air from above, producing nearly 20,000 pounds of downward thrust. Simultaneously, the rear engine nozzle, the three-bearing swivel module, 3BSM, rotates 95 degrees downward in less than 3 seconds. This mechanical movement redirects the engine's 18,000 pounds of hot thrust toward the ground. To maintain balance, 2 roll posts on the wings bleed off bypass air from the engine to provide lateral stability. In total, the F-35B generates over 40,000 pounds of vertical lift, allowing a 40,000-pound machine to hover with surgical precision. The physical environment during a vertical landing is extreme. The sound output reaches approximately 150 decibels, and the downward blast creates a fountain effect of superheated air. This heat is so intense, reaching 3,000 degrees Fahrenheit, called thermal distress, that it can buckle the steel decks of traditional amphibious assault ships. As a result, navies had to develop specialized heat-resistant coatings for their flight decks just to accommodate the jet. Defying gravity requires mechanical perfection, but this capability comes at a cost. The lift system takes up significant internal space, reducing the F-35B's fuel capacity by nearly 30% compared to the F-35A. Every vertical landing is a high-stakes calculation of weight, fuel, and temperature. But while the hardware handles the physics, a silent digital network is working behind the scenes to ensure the jet is ready for its next mission. Defying gravity requires mechanical perfection, but what happens to the carrier deck when a jet blasts it with 3,000 degrees of heat? Maintaining a fleet of fifth-generation fighters requires more than just mechanics with wrenches. It requires a global digital nervous system. Originally known as ALIS, Autonomic Logistics Information System, and now transitioning to ODIN, Operational Data Integrated Network. This software manages the health of every F-35 in the world. As soon as a jet lands, the system automatically transmits data on engine performance, structural stress, and sensor health to a central cloud. This digital architecture allows the F-35 to predict its own failures. If a fuel pump in an aircraft stationed in Japan shows a 15% drop in efficiency, the system automatically flags it and orders a replacement part from a warehouse in the United States or Europe. This real-time supply chain management aims to keep mission capability rates above 80%. A difficult target for a machine that requires roughly 30 hours of maintenance for every hour spent in the sky. The physical footprint of this logistics tale is massive. Each squadron relies on portable servers and high-speed data links to remain operational. However, this level of connectivity introduces a new dimension of warfare: cybersecurity. Because the jets are constantly talking to the global network, the Pentagon must defend against digital intrusions that could ground the entire fleet without a single shot being fired. The F-35 is the first fighter jet that can be patched with a software update like a smartphone to fix mechanical or tactical flaws. Software keeps the fleet in the air, but this same digital tether creates a vulnerability that no missile can match. The reliability of this network depends on a physical reality: a fragmented, globalized production line that spans continents. The F-35 is not just an American aircraft. It is a global industrial project. Lockheed Martin manages a supply chain that includes over 1,900 suppliers providing components for a single airframe. This international assembly line ensures that the F-35 program is too integrated to fail. For example, the center fuselage is produced in Turkey and the United States, while the wings are manufactured in the United Kingdom and Italy. Final assembly and checkout (FACO) facilities exist in Fort Worth, Texas, Cameri, Italy, and Nagoya, Japan. This fragmentation serves a geopolitical purpose. By distributing the production of high-tech components, the United States secures long-term defense commitments from its allies. However, the logistics of this system are incredibly fragile. A delay in a specialized titanium forging factory in one country can halt the entire production line 5,000 miles away. The program must manage the movement of millions of parts across oceans, requiring a level of shipping and air freight security that rivals the complexity of the jet's own avionics. The engineering standards across these 1,900 suppliers must be identical. A bolt manufactured in Australia must fit a bracket made in Canada with a tolerance of less than 0.001 inches. If a diplomatic rift or a regional conflict breaks out, the supply of critical spares could be severed, grounding fleets in weeks. This makes the F-35 as much a diplomatic tool as a weapon system. To fly the jet, a nation must remain part of the globalized Western defense infrastructure. An international assembly line ensures diplomatic loyalty, but can this fragmented system survive a real-world blockade? As the hardware moves through the world, the aircraft itself prepares to dominate a domain that has no physical borders. Block 7. The future of electronic warfare. The F-35 rarely needs to fire a kinetic weapon to neutralize a threat. Its most potent capability lies in the ASQ-239 electronic warfare suite, a system that operates across the entire electromagnetic spectrum. This suite acts as both a shield and a scalpel. It can detect enemy radar emissions from hundreds of miles away, categorize them, and then jam or spoof those signals with surgical precision. By the time an enemy operator sees a flicker on their screen, the F-35 has already mapped their location and disrupted their ability to lock on. This electronic dominance allows the jet to perform suppression of enemy air defenses, SEAD, without being detected. Instead of high-explosive bombs, the F-35 uses high-gain, multi-beam antennas to flood enemy communication networks with digital noise. The air inside the cockpit remains silent, but outside, the invisible environment is a chaotic battleground of radio frequency interference and deceptive data packets. Engineers designed this system to be future-proof, allowing the software to adapt to new radar frequencies through simple digital updates. The strategic impact of this capability is a total change in the balance of power. The F-35 functions as a quarterback in the sky, identifying targets that older F-15 or F-16 cannot see, and passing that data to them via the Link 16 network. The jet doesn't just survive in contested airspace, it transforms that airspace into a transparent map for the entire Allied fleet. In a modern conflict, the side that controls the spectrum controls the outcome. The F-35 rarely fires a shot to win. Its real power lies in a domain that is completely invisible to the naked eye. As these systems evolve, they are setting the stage for a new era where the pilot may no longer even be inside the cockpit. The F-35 Lightning II represents the end of the traditional fighter jet era and the beginning of the networked warfare age. It is a machine defined not by its top speed or its turn radius, but by its ability to harvest and weaponize information. While the costs are monumental and the logistical tail is fragile, the capability it provides ensures that the skies remain a domain dominated by those with the best software. As we look toward the future, the lessons learned from the F-35 are already shaping the next generation of air dominance, where manned jets will lead swarms of autonomous drones. Machines like this are redefining the balance of power in the skies. The story doesn't end here. Tell us in the comments. Which military machine should we explore next? Fighter jets, submarines, aircraft carriers, or secret military bases? And don't forget to tell us which country you're watching from.